Online students, can you hear me? Online students, can you hear me clearly? Online students, please confirm with a message. Okay, so let's start the class. I know it's not a very convenient day to, I know it's not a very convenient day to do a class, but I mean, I just decided to continue with the class because I anyways have to produce the recording and you anyways have to watch the recording later. So I'm just, I mean, so like if there's lightning or any kind of issue, if there's any kind of issue, if you're facing, just leave the meeting. I'm just doing the session because anyways I have to follow, I have to do the recording. That's why I'm doing the session. Okay, so let's continue. Okay, so let's start. We were just learning Poiseuille. Did we learn Poiseuille's law? Yes or no? But I think in the English medium class, no, right? Did we learn? Did we learn Poiseuille's law? Please confirm. We learned Poiseuille's law, but we didn't do any question from Poiseuille's, right? Did anyone? Were you in the English medium class last week? Friday one? No, right? Anyone who was in the English medium class? Anyone? We learned Poiseuille's law, but we didn't do questions, right? That's the idea, right? Okay, nice. So let's move forward with the questions. Okay. So what is Poiseuille's law? What is Poiseuille's law? Uh, I'll quickly remind the equation: delta Q over delta T, delta Q over delta T equals pi over 8 r to the power 4 over neta delta P over delta L. Delta P over delta L. So this is pressure gradient. This is pressure gradient. That means how the pressure changes, how the pressure changes. This is delta P. How the pressure changes with the length. How the pressure changes with the length. Delta P over delta L. We call this the pressure gradient. We call this the pressure gradient. This is r to the power 4 radius. This is neta. Viscous coefficient. Viscous coefficient. And this is how fast the liquid flow. We call this the volume flow rate, the amount of volume per second. Volume flow rate, which means the amount of volume per second. Clear? Amount of volume per second. Okay. Delta V over delta T. Okay. So let's go for questions. Okay. Let's start by exercise 2. Exercise 2. Question 5. Exercise 2, question 5. Uh, then question 3. Question 3. Question 5 and question 3. Multitudes in the Zoom chat. Question 5. A capillary tube is attached to a bottom of a large vessel. The liquid flows through the capillary tube so that the liquid level in the vessel is constant. Graph the pressure change across PQRS. Uh, So you have a system like this. Don't apply Bernoulli for capillary tubes, okay? For viscous. I mean, this is a viscous liquid, okay? This is a viscous liquid. So when we give a question like this for students, what they do is they try to apply uh, Bernoulli's law. What is the problem with applying Bernoulli? I mean, you can apply Bernoulli and try to figure out the pressure values here. Bernoulli is entirely wrong. Bernoulli works for non-viscous fluids, okay? Okay, Bernoulli works for non-viscous fluids. If you think from Bernoulli, pressure from here to here would be same. But for viscous fluids, it's not the case. Okay, for viscous fluids, if a liquid flow from here to here, there's definitely a pressure gradient, right? There's definitely a pressure gradient from here to here, okay? So this is P, this is P. We go down like this, then like this. This is Q, this is Q, this is R, and this is S. This is S. This is S. Okay. So, uh, so how the system would work is pressure with distance from PQRS. We are starting from atmospheric pressure at P. We are starting at atmospheric pressure. Clear? Starting at atmospheric pressure. Then from here to here, P naught plus H rho G, right? From here to here, it is P naught plus H rho G. Clear? Pressure increases from P naught to H rho G. Pressure increases from P naught to P naught plus H rho G. Pressure increases from P naught to P naught plus H rho G. Then this is P, this is Q. Then from Q to R, there's no reason for a pressure difference. From Q to R, there's no reason for a pressure difference, right? Because there's no flow from here to here. It's just 2 points at the same height, okay? It's just 2 points at the same height, clear? 2 points at the same height. Then from R to S, there's another pressure drop like this, clear? From R to S, there's another pressure drop like this because here we start with a higher pressure, but here it's atmosphere. So it should eventually drop to atmospheric pressure again, clear? It should eventually drop to atmospheric pressure again. This is where the Poiseuille's law applies, okay? When there's a flow in a viscous fluid through a small tube, there's a pressure gradient. Pressure gradient means a pressure drop. There's definitely a pressure drop. Clear? පීඩනය අඩු වෙන්න ඕන මෙතන ඉඳන් මෙතෙන්ට ගලාගෙන යද්දී දුෂ්ටරාවී තරලයක නම් clear? In a viscous fluid, there should be a pressure drop with the distance. Clear? That's what we call a pressure gradient. Okay? That's what we call a pressure gradient. Okay, next. Next. Moving forward, what is the next question number I asked you to try? Third one. Let's try the third one. AB and BC are two tubes of equal length, radius 2 and 1 ratio, and with uniform cross section. The axes of these are joining at B so that these are in the same line. Water enters at a pressure 105 at A end and removes at a pressure 104 at NC. It goes out at a pressure 104 at C. Find the pressure B in each case. In the second part of that, they are telling that 20% of water is damaged. It is like 20% of water is going out. There's a water leakage of 20%. at the joint B. Initially, there's no water leakage. That means you have a tube like this. You have a tube like this. Then the radius drops. Then you have a tube like this. Okay. Then we have a tube like this. Here, this is radius 2r. Here, this is radius 2r. Here, the radius is r. Okay. Then, same length, right? Same length, I hope. L, L, A, B, and C, right? Then the pressure at A is 105. Pressure at A is 105. Pressure at C is 104. 104. Pressure at A 105. Pressure at C 104. So like I can write here again what is Poiseuille's law? Delta Q over delta T equals pi over 8 r to the power 4 over eta delta P over delta L. Delta P over delta L. So here like if you have a certain delta Q over delta T here, you should have the same delta Q over delta T here too. Okay, why? Same fluid flow continues. Okay, same fluid flow continues. Okay, there's no leakage or anything like that. So the same fluid flow should continue. Clear? Okay. So as a result, you can write from here to here delta Q over delta T fluid flow rate delta Q over delta T equals pi over 8. Here the radius is 2r to the power 4 over eta. Delta P is, here the pressure is 105. Here the pressure I'll write as PB. So it is 105 minus PB. It is 105 minus PB divided by length. Then you should have the same fluid flow. Then you should have the same fluid flow from here to here. So you can again write Poiseuille's law pi over 8. Now the radius is not 2r, it is r. So r to the power 4 over eta. Pressure difference from here to here is PB minus 104 over this length is L. So when you try to solve this, when everything cancels out, pi over 8, r, eta, L, everything cancels out. What is left is only 2 to the power 4. Here you have 2 to the power 4 left here. Then 105 minus PB here. PB minus 104. You solve this, you get PB, okay? You solve this, you get PB. Clear? So I remind again, like if you have lightning or any kind of issue, just leave the meeting. I'm just doing the session because anyways I had to produce the recording because many students would be watching the recording. So I anyways have to produce the recording. That's why I'm doing the session. But if you have any issue with joining or lightning kind of stuff, just leave the session, okay? We get PB equals 104.9. PB equals 104.9. What is the unit? What is the unit? Newton per meter squared. Newton per meter squared. Clear? That's how you get the answer here. Okay. That's how you get the answer here. Then try to get the answer for the 20% loss. If there's a loss of 20% at B, try to get the answer. If there's a less loss of 20% at B, so if there's a 20% loss, there's only one difference. What is that? If there's a 20% loss, if there's only one difference, what is that? This is the initial flow. This is the initial flow. That means the flow that go from here to here. Then here there's a leakage of how much? 20%. So only the remaining 80% will continue to flow in this tube, right? Only the remaining 80% will continue to flow in this line, right? So you get the initial fluid flow, then you multiply it by 80%. Only the remaining 80% will flow in this. That means will be equal to this, clear? So you get a additional 80% here, then you solve. That's all. That's the only difference, clear? You get a, when you solve everything, pi over 8, r, neta, everything cancels out. You get an additional 80%, clear? That is the idea. Okay. That's the idea. So let's move forward. let's move forward. Stokes law. Stokes law. I'm gonna skip the practical and go for another small theory part. Okay. In Poiseuille, this is all you could get. Okay. I mean, when we are doing past papers, you would see again the same concept repeats. Okay. Nothing new, nothing complex, just the same concept repeats again and again. Okay. When we are doing past papers, you will see that. Then the Stokes law. Now we have discussed, I mean, in this lesson, what we are doing is we are just analyzing some practical scenarios that may appear. We are just analyzing practical scenarios that may appear due to viscosity. Okay. We are just discussing practical scenarios that may appear due to viscosity. That's all. Okay. So here we discussed what happens when liquid flows as layers, like a boat. When a boat going above water, it feels a viscous force. These kind of scenarios we analyze. For that we use Newton's law of viscosity. Then now we analyzed behavior of a flow happening in a tube. Next we analyze behavior of a flow happening in a tube using Poiseuille's law. Now another practical scenario is, what about something like a submarine? An object going through a liquid, not above, not at the highest layer like a boat, no, through a liquid. When an object goes through a liquid, okay. For this we use Stokes law, okay. For this we use Stokes law, okay. So when something goes through a liquid, okay, when something goes through a liquid, you definitely feel a opposite viscous force, okay. You definitely feel a opposite viscous force. What is the value? F equals 6 pi neta Ru. Clear? F equals 6 pi neta Ru. You definitely feel a opposite viscous force. Clear? You definitely feel a opposite viscous force. 6 pi neta Ru. Clear? Okay. What is this equation? This is Stokes law. This is Stokes law. How do we prove this? We have to use dimensional analysis. That means when anything moves through a liquid, we know that there will be a drag, right? Even when you take your hand through a liquid, when you move your hand through water, definitely you will feel a viscous drag, right? You will definitely feel a viscous drag. So when you consider this viscous drag, okay, when you consider this viscous drag, we found that it depends on definitely on the velocity of the object, size of the object, and viscosity of the liquid, okay. But since we are analyzing the simplest model, which is a sphere, okay, I mean here we are learning the syllabus in a theoretical manner, okay. We are just learning the syllabus in a theoretical manner. Clear? So instead of analyzing a very non-uniform object like a submarine, we are just analyzing the theoretical aspect, which is a sphere, okay. So we apply dimensional analysis to this, okay. We apply dimensional analysis to this. When we apply dimensional analysis, we get a viscous drag of, I mean, I'm not going to do the dimensional analysis part, 6 pi neta Ru. So this is just another force, okay. So if something goes down in a liquid, it will now, initially it felt its weight and upthrust only. But now when it is going down, it will feel the viscous drag of 6 pi neta Ru2. 6 pi neta Rv. V is velocity. Clear? Initially, before were doing questions, we considered weight and upthrust only. Now there's a third force, clear? Same thing when it is going up. You have the weight down, mg, and you have the upthrust up. If it is moving up with a certain velocity, it has a viscous drag of 6 pi neta ru. Clear? 6 pi neta r actually v. Clear? Clear? So the next part I ideally need to teach, okay? But before that, I'll let you try a question, okay? I'll let you try a question just for the sake of thinking, okay? Just for the sake of thinking. This is a part that I should teach. When I teach and give this question, it's pointless, okay? Because in the next theory part, we are learning everything required for these questions, so there's no thinking involved then. So I need you to try exercise 3 question 6 first, okay? I need to try you to try exercise 3 question 6 first, okay? First try that, okay? But don't worry if you can't get the answers. It's just for the sake of thinking. Otherwise, I have to teach that part. Check. Uh, so I'll do this question. So don't worry about the question. This is not actually for, I mean, just for thinking, okay? Because when I do the theory part, then this is everything is included in theory. So there's no point, there's nothing left to think after that, okay? That is the reason. There's nothing left to think. That's why. So if I take this scenario, uh, find the tension of the string, like when you're trying to find the, now I need you to think with the equation, okay? When you're trying to find the tension, do you have to worry about viscous force? No, why? Viscous force appears when you have a velocity, okay? Viscous force appears when you have a velocity only, okay? So there's no velocity means there's no viscous force, okay? So like that you have to think, okay? So here you have only the weight, only the weight. What is the weight? Volume, volume, V. I'll just write volume as V. Density, density, density of the object, rho, density of the object, rho, G. This is the weight, V rho G, clear? Then what about the upthrust? What about the upthrust? You get what? V sigma G. V sigma G. Density of the liquid is sigma, clear? And you have the tension, clear? Now this is under equilibrium, okay? This is under equilibrium. So you write, you have V sigma G up, V sigma G up, and you have V rho G, V rho G, and tension down. V sigma G up, V rho G, and tension down. Clear? Clear? V sigma G you have up, you have tension and V rho G down. Clear? So you can write tension equals, you can write tension equals V sigma minus rho G. You can write tension equals V sigma minus rho G. Clear? So this is the tension. Clear? This is the tension. Then the next part, I mean, I can even write V as 4 over 3 pi r cube. This is a sphere. So 4 over 3 pi r cube sigma minus rho G. Sigma minus rho G. Clear? 4 over 3 pi r cube sigma minus rho G. Four over 3 pi r cube sigma minus rho into G. This is the tension. Second one, find the acceleration at which the sphere begins to move as the string breaks. So definitely when the string breaks, this tension may disappear. So that will be the resultant force, right? This tension will disappear. That will be the resultant force, right? So what is the acceleration? F equals ma. When you cut the string, the tension will appear as the external force above, right? In upward direction. So you can write 4 over 3 pi r cube sigma minus rho G equals ma. Clear? Equals ma. Again the volume 4 over 3 pi r cube. To get the mass, you need to multiply by the density of the object. Density of the object is rho. Density of the object is rho. Then a. Acceleration is a. Then 4 over 3 pi r cube cancels out. 4 over 3 pi r cube cancels out. You write acceleration equals sigma minus rho G over rho. Sigma minus rho over rho into G. Clear? This is the acceleration. Clear? Then the third one, find the terminal velocity. What is the terminal velocity? What is the terminal velocity? I'll write the third one here. Terminal velocity is something like this. Now this will start accelerating, right? Now this will start accelerating. When it accelerates, you have the upthrust here, weight here, and when it accelerates, it gains a velocity. When it gains a velocity, it will gain a viscous force of 6 pi neta RV. It will gain a viscous force of 6 pi. It will gain a viscous force of 6 pi neta RV. Clear? Slowly it will gain a viscous force of 6 pi neta RV. Clear? So you can write upthrust U equals downward you have mg and 6 pi neta RV. Okay, I mean not like this. I mean what will happen is now if I apply F equals ma to this one, it will have upthrust above, mg downwards, and viscous force 6 pi neta RV down equals ma. Now here what happens is, properly try to understand, now the velocity increases, right? Velocity increases, clear? Velocity increases. When the velocity increases, it's a negative part. So when velocity increases, acceleration will decrease, right? When velocity keeps increasing, acceleration will keep decreasing. So after a certain point, at a certain velocity, this side will be equal to 0, right? At a certain velocity, this side will be equal to 0. That means this one keeps gaining magnitude. At a certain point, it will match this, and the equivalent will be equal to 0. That means resultant velocity becomes 0. Resultant acceleration becomes 0. No acceleration. That is the maximum possible velocity this one can get, right? That we call the terminal velocity. Anta pravega. Clear? The maximum possible velocity in the system. Clear? The maximum possible velocity in the system. Clear? That is the maximum possible velocity in the system. V terminal. Clear? We call this the terminal velocity. Clear? We call this the terminal velocity. Okay. So what happens now is now you have a terminal velocity. Okay. Now you have a terminal velocity, V terminal. Clear? So that is the maximum possible velocity you can get. Why? This system keeps accelerating, but the acceleration decreases. At a certain point, the acceleration stops because the velocity is too fast such that it cancels out other forces and the acceleration becomes 0. Then you have the terminal velocity. So you can get the terminal velocity when this is equal to 0. When u minus mg minus 6 pi neta r v is 0, v becomes terminal velocity. Okay, that is the terminal velocity. So I can write v terminal as u minus mg divided by 6 pi neta r. U minus mg divided by 6 pi neta r. Okay, then u means 4/3 pi r cube, volume V, volume. Density of the liquid is sigma. Density of the liquid is sigma, right? G minus, what is the weight? 4/3 pi r cube rho g. 4/3 pi r cube rho g divided by 6 pi neta r. Clear? 6 pi neta r. Clear? So pi cancels out. Pi cancels out. R cube cancels out with this and becomes r squared. Becomes r squared. This 6 will cancel out and this will become 2 and this will become 3. Here will again you get 2. Then when you solve this you would get here pi also cancels out with this. Then you get 2 over 9. 2 over 9. Here you have r squared over neta. Then here you have sigma minus rho. Sigma minus rho into g, right? Clear? Clear? Check my calculation. Is this correct? Same thing did you get? Yes, right? This is the terminal velocity. Okay. This is the terminal velocity you get. Maximum possible velocity you get. So next we are going to learn terminal velocity as a topic. Maximum acceleration as a topic. We are going to learn everything as topics. Then no point of doing the questions. That's why I started with questions. Because these are actually theory points. Okay. So we are going to learn these things as theory. So after that, there's no point of doing questions. Okay. That's why I first do this. Write down if you have to write anything. Okay. Next. If 1 over 10th of energy loss occurs when the sphere rises above the water surface, find the velocity at which the sphere enters air through water surface. So now what is happening here is, now when this reached its terminal velocity, is anyone writing this? Just mention in the Zoom chat. Is anyone writing this? Is anyone writing this? Mention in the Zoom chat quickly. I need to move forward. Because today I'm planning to finish theory. Anyone? Anyone? It's a good day to sleep, right? Had the same plan, but I have to do this today because I don't have any other day to finish this. Uh, Anyone? No, right? Looks like there's no one. So now when this obtains the terminal velocity, okay, when this obtains the terminal velocity, it just continue with that velocity, okay? After obtaining the terminal velocity, it just continues with that velocity, clear? It just continues, okay? After obtaining the terminal velocity, it just continues. So it will even reach the air surface with the same velocity, okay? With the same velocity, but they are telling that there's an energy loss of 1 over 10, right? Clear? There's an energy loss of 1 over 10. That means, what is the kinetic energy here? Half m Vt squared. When we lose 1 over 10th of energy, remaining is 9 over 10, right? Remaining energy would be 9 over 10, and that would be the velocity it obtains when it goes out of the surface. That would be the velocity it obtains when it goes out of the surface. Half mv squared. Clear? Half mv squared. So m cancels out, half cancels out, v equals 3 over root 10, 3 over root 10 v terminal. V equals 3 over root 10 v terminal. Clear? This is the velocity. This is the velocity and this is v terminal. Okay, you put that there. Okay, this is v terminal. Find the height at which the sphere rises in the air. Now this is a motion equation question. Okay, now this is a motion equation question. So it goes up with a velocity of v1. This velocity is v1. At the highest point it stops and the height is h. So we write v squared equals u squared plus 2as. At the highest point the velocity is 0. Starting velocity v1 squared plus 2. Acceleration minus g. Acceleration minus g. When it goes up we have acceleration of minus g and the height is h. Height is h. Then h becomes v1 squared over 2g. Height becomes v1 squared over 2g and this is v1. Okay, this is v1. Clear? Clear? So after that it's a motion question. Now draw the graphs. It's a very important part. Again it's a theory. Okay, it's a theory. We are going to learn that as a theory point. Okay, so it's again a theory. So you will learn that. You don't have to worry about this, but when I teach it as a theory there's no point of doing these questions. That's why. Try to draw the graphs. I'll put the tut in the Zoom chat. Put the tut in the WhatsApp groups too. I mean, you don't have to think about the potential energy here, okay? when it is going in this path, it's a constant velocity, right? From force, when you consider force, it's a constant velocity, okay? So you don't actually have to worry about potential energy. What actually happens is, uh, yes, you are gaining potential energy, okay? You are gaining potential energy, but upthrust is providing that work. Upthrust is providing that work. So when you do the question from the aspect of forces, you don't have to worry about energy, okay? You either do a question considering energy, or you either do a question using forces, okay? So if you were considering energy, you have to consider the work done by upthrust, potential energy increase, negative work done by the viscous friction force. You consider everything and you apply more, you apply force, you apply energy equations, then you will get the same set of answers, okay? When I apply F equals ma and get the acceleration and do the question, I don't worry about energy. It's just two ways of doing the same question, okay? So when you're applying F equals ma and getting that the acceleration is 0, then you do the question, then you don't worry about energy, okay? So let's move forward. Question 6, the graphs. Graphs. Question 6, the graph. Talking about the graphs, first let's draw the acceleration graph. So you have to understand acceleration starts with a high value, right? Initially you have a good acceleration when you cut the string. But then when you keep gaining velocity, acceleration decreases and acceleration drops to 0. Acceleration keeps decreasing and acceleration drops to 0. Clear? When you keep gaining velocity, acceleration decreases and acceleration drops to 0. Clear? Acceleration decreases and acceleration goes to 0. Clear? This is when you obtain the terminal velocity. Clear? When you obtain the terminal velocity, acceleration goes to 0. Acceleration disappears. Then what happens to the velocity? What happens to the velocity? Velocity increases, then become constant here. Okay. Velocity increases, velocity keeps increasing, then become constant here. Okay. Why? You have an acceleration, it goes down and disappears. So velocity increases due to acceleration, but here velocity becomes constant. Clear? Velocity becomes constant. You get a constant velocity here, which is the terminal velocity. Clear? Which is the terminal velocity. Okay. This is the terminal velocity. Then after that, the displacement. After that, the displacement. Displacement. Displacement keeps increasing and velocity keeps increasing. Velocity keeps increasing, so the both displacement and the gradient keeps increasing. Okay. Why? Velocity is the gradient of a displacement time graph. So velocity increases means displacement increases, and at the same time gradient increases. Then here velocity becomes constant. That means the gradient becomes constant. That means the gradient becomes constant. Clear? Velocity becomes constant. That means the gradient becomes constant. Clear? Gradient becomes constant. Got the idea? Ah. They are talking about until the maximum height. Okay. Sorry. Then what happens? Then now this is until it's going in water. Okay. Now it goes through water and comes out. Okay. When it comes out, it feels gravity. Okay. When it comes out, it feels gravity downwards, right? Clear? That means acceleration goes negative. Clear? Acceleration goes negative. Suddenly acceleration becomes minus g. When you come out of water, acceleration suddenly becomes negative g, minus g. Clear? Because you feel gravity. Okay. What happens to the velocity? Actually, this is not how the graph should look like. Why? First, you go a certain distance with terminal velocity. Then only you come out of water. Then you feel gravitational acceleration minus g. Clear? Then you feel gravitational acceleration minus g. Initially, you had acceleration up. Then acceleration goes to 0 and you obtain terminal velocity. Then you feel gravitational acceleration. Then what happens to the velocity? What happens to the velocity? You have a sudden drop of velocity when you come out of water. 1%, sorry, 1 over 10th decrease of velocity energy. So when you come out of water, there's a sudden drop. Then after that, you feel gravitational acceleration and you go up and eventually become 0. Velocity eventually becomes 0. Same thing happens with displacement. Same thing happens with displacement. Same thing happens with displacement. You go like this. Then after that, velocity is decreasing. That means gradient is decreasing. Velocity becomes 0. That means gradient of the displacement time graph becomes 0. Clear? Velocity becomes 0. So the gradient of the displacement time graph becomes 0. Clear? Got the idea? I mean, just don't worry. We'll do this next as a theory, everything. But I need you to try to understand this, okay? Ask if you have any questions. Okay. So now let's learn this as a theory, okay? Now let's learn this as a theory. So the idea is this. Assume that first you drop a steel ball inside a liquid. So when this moves down in that liquid, it will go down due to its weight. So motion of a spherical object through a viscous media, there's a topic like that immediately after Stokes law. That's what I'm talking about. So in this example, they are giving the density of the material as sigma, density of the liquid as rho. Just don't confuse this with the previous question. In the previous question, they give this as rho and this as sigma, okay? Don't confuse that. So, so you have the weight downwards, mg. Mg means v sigma g. Then you have the upthrust u, which is v rho g. Then you feel the viscous force. Which is 6 pi neta rv, given that the velocity is v. Clear? Given that the velocity is v. Clear? So, in this system, okay, if you apply like F equals ma, you will feel the weight downwards, V sigma G. You will feel the upthrust upwards, V rho G. Then you will feel the viscous force upwards. Viscous force acts against the motion. So in the previous question, the object was going up. So the viscous force was down. Now this is going down. So the viscous force is up. Okay. So V rho G minus you have the viscous force, which is 6 pi neta RV equals MA. M is mass. That means V sigma. Mass means V sigma. Then acceleration is A. So the acceleration is V sigma G minus V rho G minus 6 pi neta RV. So don't confuse. This V is volume. This V is velocity. So I'll consider this velocity as V1. This is volume V. V sigma G, V rho G, 6 pi neta R V1, and you divide it by V sigma. Ah. So this is the acceleration you have. Clear? This is a negative term. When will you have your maximum acceleration? When will you have the maximum acceleration? You will have the maximum acceleration when V1 is 0. That means at the beginning. When you just drop this. Clear? You will have the maximum acceleration when you just drop this, okay? When V1 is 0. Clear? When V1 is 0, you will have the maximum acceleration. So you get, when V1 is 0, you get maximum acceleration. That means when you just drop the ball in liquid, you get V sigma G minus V rho G. So when the velocity is 0, this part becomes 0. Then you have V sigma. Then V cancels out. Then you have sigma minus rho over sigma into G. Sigma minus rho over sigma into G. Clear? Sigma minus rho over sigma into G. This is the maximum acceleration. Clear? This is the maximum acceleration. Sigma minus rho over sigma into G. This is the maximum acceleration. Then uh, then after that what happens? Back to this equation. Now, after a certain time, velocity will keep increasing bit by bit, right? Due to this acceleration you have, velocity will slowly increase. So the velocity increases, since this is a negative term, acceleration will slowly decrease, clear? Acceleration will slowly decrease, clear? So acceleration will decrease, so you will have a certain acceleration, then acceleration will keep dropping down. Acceleration will keep dropping down, clear? Acceleration will keep going down, clear? It will continue to go down. And eventually, acceleration will become zero at a certain velocity, clear? What is that velocity? When acceleration is zero, you will get V sigma g minus V rho g minus 6 pi neta r. This velocity we call the terminal velocity. When the acceleration is zero is terminal velocity. Clear? So you solve this, you can get the terminal velocity. Okay. What is terminal velocity? Multiply by V sigma, that part disappears. So V terminal becomes V sigma minus rho g divided by 6 pi neta r. Then you get, what is the volume? 4 over 3 pi r cube. You get 4 over 3 pi r cube. That is the volume. Then sigma minus rho g 4 over 3 pi r cube sigma minus rho g. Then here you have 6 pi neta r. Here you have 6 pi neta r. Clear? So when you solve this, you will get a terminal velocity of pi cancels out 2 over 9 r squared over neta sigma minus rho g. This is the terminal velocity. Clear? This is the terminal velocity. Clear? This is the terminal velocity. That means when the acceleration decreases, see, although the acceleration is decreasing, acceleration is still positive, right? So velocity is increasing. But acceleration decreases, so the gradient should decrease. Then the acceleration will be zero. That means the gradient of the velocity time graph will be zero. Clear? Clear? Gradient of the velocity time graph would be zero. Clear? Next one. So this is the idea, okay? This is the idea. Then what will happen to the displacement? Everything is included in your tute. You don't have to write anything. What will happen to the displacement? When velocity increases, displacement also increases, okay? When velocity increases, displacement also increases. Clear? Then velocity will be constant. That means displacement will be constant. Clear? Sorry, then velocity becomes constant. That means gradient will be constant. Velocity increases, gradient increases. Velocity constant, gradient increases. What happens to the velocity happens to the gradient. Clear? What happens to the velocity happens to the gradient. Clear? Okay? Clear? That's why I did the question first. Okay? And everything will change a bit when it is going up. When the object is going up, these components will change, right? Clear? So if the object was going up, you can see it is included properly in your theory tute. So 2 over 9 r squared over neta. When if this is going up, you will have rho minus sigma g. Okay? Why? Object will go up if rho is larger than sigma, right? If rho is larger than sigma, object will go up. That means the density of the liquid should be larger than the density of the object. Then only it will go up. Clear? So if the object was going up, if you do all the calculations again, You will get the same graphs, same equations, but rho and sigma will change. Clear? Rho and sigma will change. Clear? Okay. Okay. Clear? So now is the theory part clear? Okay. Is the theory part clear? Okay. So that's about the theory. Okay. But one more thing to add. Okay. One more thing to add. Uh, like in a system like this. Okay. We can't apply Stokes law to any system. Okay. There are some requirements. What are the requirements? If the object is moving in a liquid. Okay. If the object is moving in a liquid. Okay. Uh, one thing is the liquid area should be infinitely large. What is the meaning of that? This movement of the object should not affect the liquid system at large. It should be, see, in the deep sea and a submarine, movement of the submarine won't affect the sea, right? Like that, the liquid system should be large, okay? Because it can't affect the layers. But think that if a sphere like this moves in a small tube like this, then it will make everything turbulent, right? Okay, it will make everything turbulent. Then you can't apply. Why? You need the liquid to stay in a streamline state. Okay, you need the liquid to stay in a streamline state. Clear? So the liquid should be in a streamline state, and it should be a large system. So due to that reason, you can't have very high velocities. Okay, why? If you have an extremely high velocity, again the system will be turbulent. So you can't have very high velocities. Okay, so the system should be streamlined and system should be large. Clear? It should be in a layered nature. Okay, it should be in a layered nature. Clear? Okay, so that's all about the theory of this lesson. Okay, that's all about the theory of this lesson. Next we have to move to surface tension. Okay, you need the interval now, but you have to go until 1 then. Okay. Okay, next what we have to do is we have to do questions. Okay, so let's move to exercise 3. Exercise 3, question 1. Question 2, question 5. Question 2, question 5. Yeah, let's mainly do these questions. Okay, and ideally question 7. Let's mainly do these questions. If you have time left, try 9 and 10 too. But these questions I'll keep them for maybe for a next session. It will won't happen next week. I'll let you know. But today we will finish theory. Then practicals I can provide a recording for further question discussions and past paper discussions. Let's arrange a date. Okay. So you can try them. I'll give the interval then. Okay. Uh, so I'll start at try to be here by 10. 25 at least and start doing the questions, but I'll start the discussion at 10:30. Okay. Try to do questions. Okay. So let's start the discussion. Exercise 3, question 1. The terminal velocity obtained by a sphere of radius a in a viscous medium is v. What is the velocity that sphere with radius 2a obtained in that medium? Exercise 3, question 1. Exercise 3, question 1. Terminal velocity obtained by a sphere. So, in a case like this, just directly use the equations, okay? What is the terminal velocity? 2r squared 9 neta, either rho minus sigma or sigma minus rho, depends on whether it's going up or down, into g. So they are telling that there's a sphere with radius a, velocity is v. Velocity is v, radius is a. Velocity is a. Then they need us to find the terminal velocity when the radius is 2a. So quite simple. You just put 2a here. You just put 2a here. That's all. Everything else is same. Neta is same. Sigma minus rho is same. G is same. Everything else is same. So this is 1. This is 2. 2 over 1. 2 over 1. What is 2 over 1? 2 is V1. And this is V equals here. I mean, when you divide this by this, everything else would cancel out. Only thing left would be this 2 squared, right? Everything else will cancel out. When you divide this by this, everything else will cancel out. You will have 4 remaining. That's all. 2 squared remaining. That's all. So V1 becomes 4V. That's all. Okay. V1 becomes 4V. It's simple like that. Okay. Let's go to question 2. So the next part also the same. Let's go to question 2. Let's try question 2. Quickly write this down if you have to write anything. Okay. Next one. Next one. We just did the first one. Question 2. First one is not a big deal. Let's go to question 2. Question 2. Exercise 3, question 2. Terminal velocity of a raindrop falling through air is V. So this is a raindrop. Velocity is V. Find the terminal velocity of a raindrop formed by combination of two raindrops. Okay. So this is the idea. If the radius is R, what is terminal velocity? Equation for terminal velocity is 2 over 9 R squared over neta. 2 over 9 R squared over neta, rho minus sigma rho minus sigma over g. So this is the terminal velocity. Now the two raindrops combine together. Two raindrops combine together, they will create a large radius. They will create a large radius. What is that radius? So volume of one raindrop is 4 over 3 pi r cube, and you consider two of them. You consider two of them. Then it is equal to 4 over 3 pi capital R cube. 4 over 3 pi capital R cube. So you get R cube equals 2 simple R cube. Then R equals 2 1 over 3 and R. 2 1 over 3 and R. Clear? So the new terminal velocity Vt dash, new terminal velocity Vt dash would be 2 over 9. Instead of R, now you have this 2 1 over 3, 2 1 over 3 R squared over neta rho minus sigma g. So this is 1, this is 2. I'll divide 1 by 2. I'll divide 1 by 2. Then everything else will cancel out. Vt dash over Vt equals Vt dash over Vt equals, only this part will remain 2 1 over 3 squared. Only that part will remain. Everything else will cancel out. Okay. Everything else will cancel out. Okay. When you divide this by this, everything else will cancel out. All you have is that, right? All you have is that. So you get Vt dash equals 2 2 over 3 Vt. 2 over 3 Vt, which means 2 over 3. What is Vt? What is the terminal velocity? What is the terminal velocity? Initially it was given as V. Initially the terminal velocity was given as V. So this is the new velocity. Clear? Clear? So the next two parts same, right? You just find the new radius and apply for the equation. Okay? You just like find the new radius using volumes, then apply to the equation. Okay? Go to question 7. Sorry. Go to question 4. Go to question 4. Try question 4. Okay. Okay. Question 4. A spherical raindrop of radius A falls through air at V naught velocity. Okay. Let's say, is anyone writing this? Anyone writing this? Mention in the Zoom chat. If you need time to write this, mention in the Zoom chat if you need time to write this. Looks like no, right? Okay. So, fourth one, a spherical raindrop, radius A, falls through air at V naught velocity. At V naught velocity. Ideally, this is terminal velocity, right? Otherwise, they would give acceleration too. If two such raindrops combine to form a spherical raindrop again, draw the terminal velocity obtained and the velocity time graph corresponding to its motion. When two of them combines, same thing, right? Same as the previous one, right? Clear? Clear? See? When two of them combines, this is the new terminal velocity, right? Clear? Just before in the second question, we did this one, right? So if the terminal velocity is V naught, when two of the droplets combine, terminal velocity becomes this 2 over 3 into V naught. 2 over 3 into V naught. Clear? 2 to the power 2 over 3 into V naught. Clear? 2 to the power 2 over 3 into V naught. This becomes terminal velocity. Clear? This becomes terminal velocity, new terminal velocity. So there's no point of giving this question because it's the same question like before. But what I needed to do was drawing the graph. Okay, why? They are not asking you to graph the terminal velocities. Okay, if you graph the terminal velocities, it's just like this. They are talking about this combines, then again separates, right? In the question. So in that case, you will have V naught. Then you will have this is larger than 1, right? Then you will have a higher terminal velocity. Then again the terminal velocity will drop. Okay, clear? If you draw the terminal velocity, it would look like this. But velocity can't jump from here to here. Okay, they are not asking you to draw the terminal velocity. They are just asking you to draw the velocity. Okay, they are just asking you to draw the velocity. Okay, so in that case, you will have the terminal velocity V naught. Okay, then when two drops connect with each other, still the velocity is this. But it can go to it have the ability to reach to a higher terminal velocity. So it will start increasing like this and eventually reach that terminal velocity, which is 2 over 3 V naught. It will eventually return a higher terminal velocity. Clear? Then again, after a certain time, they will separate. When they separate, they need to return to this terminal velocity again. Slowly they will decelerate and return to this terminal velocity again. Clear? What actually happens is, if something has a smaller velocity than the terminal velocity, its force is larger than, other forces are larger than the friction force, viscous force. So it will accelerate and reach the terminal velocity. If something has a higher velocity than its terminal velocity, if something has a higher velocity than its terminal velocity, okay, if something has a higher velocity than its terminal velocity, its viscous friction force is higher, its viscous friction force is higher, so it will start decelerating and reach a constant velocity. Clear? It will start decelerating and reach the new terminal velocity. Okay, so you can have a higher velocity than terminal velocity or lower velocity than the terminal velocity. What happens is, if your velocity is lower than the terminal velocity, you will accelerate and reach the terminal velocity. If your velocity is higher than the terminal velocity, you will decelerate and reach the terminal velocity. Okay, so given enough time, any system eventually would turn into the terminal velocity. Okay, that is the idea. Clear? So what we would do is you can try other questions. Okay, I'll arrange a day to discuss the remaining questions from all three parts. Okay, maybe an online session. Okay, maybe an online session. I'll try to arrange an online session. Okay, I'll try to arrange an online session to discuss the remaining questions in all the exercises and to do some past papers. For practicals, I can provide a proper practical recording. So we can today finish the lesson, theory and all. But to do some other questions and past papers and all, I'll arrange an online session. I'll inform about that. Okay. 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 So next, let's move to surface tension. New topic. Let's move to surface tension. Please try other questions as homework and I'll arrange a separate day to do all other questions. Okay. Today the main target is teaching the theory parts. Okay. And I think some students are getting this for their term test too. Okay. So I'm working with the focus of finishing theory first before doing a lot of questions. Then let's move to the questions next. Okay. Let's go with that plan. Okay. Let's move forward. Next topic, surface tension. Surface tension. What is surface tension? What is surface tension? Okay. Uh, Usually what is tension? Tension is the elastic nature of any object, right? Tension is a force that appears due to the elastic nature of an object, right? When you stretch a string or a spring or a rubber band, due to elasticity, it creates a tension. So liquid doing the same thing is surface tension, okay? When liquid does the same thing, you have what? You have surface tension. Before that, before understanding surface tension, we have to learn about cohesive forces and adhesive forces. Okay, what is the meaning of that? Sanshakti bala, ashakti bala. I mean, it's like this. When a liquid, when a liquid particle is inside the liquid, when a liquid particle is inside the liquid, it is surrounded by, it is surrounded by other similar particles, right? Other similar particles. Clear? When a liquid is when a liquid particles is inside a liquid, it is surrounded by other liquid particles. So all the forces from all the sides is same, right? You feel similar forces from all the sides. Clear? You feel similar forces from all the sides. So eventually all the forces will cancel out. Okay, eventually all the forces will cancel out. Clear? Eventually all the forces will cancel out. So any particle can stay peacefully here. But going to the surface is not simple like this. Going to the surface is not simple like this. Why? When you reach to the surface, okay? When you reach the surface, okay? Clear? When you check this circle, here there's a certain distance that other particles can affect this particle. That means only a particle with a certain distance will affect this, okay? I mean, particle here will not affect here, right? Only the close by particles. So this sphere with that distance, we call that the sphere of influence. Balaimi Golaya, sphere of influence. The sphere that, I mean, other particles should stay here to influence this. So in liquid, everything in the sphere of influence is the same liquid, so no resultant force because everything is same. But when a particle reaches to the surface, in this side of the sphere of influence, you have liquid particles which provide a strong force, clear? In this side, it's just air, no force, clear? In this side, it's just air, a very weak force, very weak force. That means when something try to reach the surface, okay, when something try to reach the surface, it starts feeling a downward drag. It starts feeling a downward pull, clear? It starts feeling a downward pull. So it can reach the surface only by fighting with this force. Okay, just like a spring, just like a spring, just like moving against a spring, clear? Just like moving against a spring, clear? So even in a spring, when you stretch or when you move against a spring, that work you have to do for that stores in the spring as potential energy, as elastic potential energy, right? The work you do against the springs gets stored as elastic potential energy, right? So in this case also, the work this particle does when moving from here to here is stored as a potential energy in the system. It is stored as an energy in the system. So more particles on the surface, more energy system contains, okay? More particles on the surface, more energy the system contains, and it is not good. Why? Any natural system likes to stay in the lowest possible energy state. That's why water flows from up to down. Why? Why? They need to attain a smaller potential energy. Okay? That's why when you release a spring, it tries to return to reach the smallest elastic potential energy. Any natural system would try to stay as neutral as possible and at a lowest possible state of energy. Clear? Any particle would try to stay, any natural thing would try to stay in a lowest possible state of energy. So for this liquid, the option is to reduce the number of particles of the surface, reduce the surface area. Why? The more particles you have on the surface, more energy you contain. Clear? Why each particle to reach the surface have to do a work, it is stored as energy. So any liquid tries to minimize its surface area. So the shape with the smallest possible surface area in the world is sphere. For a given volume, it's mathematically proven for a given volume. The shape with the smallest possible surface area is sphere. That's why liquid, whenever possible, try to be spherical. That's why when water drops, it's not square shaped, it's spherical. Clear? Clear? Liquid always try to reach a spherical shape. Clear? Spherical shape to minimize the surface area. So even a normal liquid in a container like this would try to keep at least a small spherical shape like this to minimize the surface area. Clear? Just think if you have a bunch of springs connected like this to particles, and if you stretch all these particles away, what will be the shape? It will be shaped like this, right? It will be shaped like this, right? Clear? If you get catch a bunch of particles like this and try to stretch this, it will try to come up with a shape like this. Same thing happens here. So due to this reason, any surface to when it keeps this shape, that surface will be stretched. That means it's not peaceful like this. This is a stretched shape. How can a liquid keep a stretched shape like this? By creating tensile forces, tension forces among the particles on the surface. So it works as a membrane, rubber membrane. Okay, okay. They are creating a tension between each other, and it will act as a membrane. And so in this surface, there will be a tension. There will be a tension. This tension forces that appear here, we call the surface tension. Clear? So the idea is any liquid need to minimize its surface area. So it try to be spherical as much as possible. For that, it has to take that shape. For that, it use its intermolecular forces and create a tensile force on the surface and act as a membrane. Okay. That force appears between the surface particles. To keep this shape, we call it the surface tension. Clear? We call it the surface tension, but the thing is, still the surface tension is quite logical. We know how it acts, how it happens, but not mathematical. We need to quantify this. Okay. If someone asks you what is the surface tension here, it is zero. Why? Tension itself is an internal force, right? So if you focus at a certain area, you have the both action and reaction, right? See, so tension, anyways, tension everywhere, it is an internal force, right? Clear? Tension is always an internal force. Clear? So it will be stretched like this. Clear? It will be stretched like this. Clear? So you can't calculate the surface tension like this because it is an internal force. Clear? So we bring a new mathematical format to learn or analyze this surface tension. If this is the liquid surface, we draw a imaginary line on the surface. We draw an imaginary line on the surface. So on this imaginary line, tension may appear in both in this direction and both in this direction, right? Tension may appear both in this direction and this direction. Clear? Clear? So what we do is, we tell, forget this, draw a, draw a, draw an imaginary line, draw an imaginary line of a length 1 meter. Length 1 meter. Draw an imaginary line, length 1 meter. Then consider all the perpendicular forces, only the perpendicular components of the forces acting only in one direction. Clear? Sum of all these forces, we gave it the name surface tension coefficient. That's how we model the surface tension. Clear? How? Otherwise, we can't quantify it. We get a liquid, any liquid, draw a 1 meter imaginary line on the surface, then consider the sum of the perpendicular forces acting on one direction. Sum of these perpendicular forces is surface tension coefficient. Clear? That's how we define the surface tension coefficient. Clear? Now you have a method. Why? Now, if you have an object like, if you have a liquid surface like this, if you keep a pencil here, length L, what will be the total surface tension force acting on this pencil? T is the force on unit length. T is the force on unit length. Then the force on a length L is TL. Force is what? Force is TL. Clear? Surface tension coefficient into length. Clear? Force is TL. Clear? Next. Considering like another thing is, we know that elasticity and viscosity changes with temperature like this. Okay, both decreases with temperature. Clear? Even surface tension also decreases with temperature. Okay, Even surface tension coefficient decreases with temperature, but not like this. Like this. That means it goes down and entirely disappears after a certain temperature. Okay. It decreases and entirely disappears after a certain temperature. Clear? So the viscosity and elasticity behaves like this, but surface tension behaves like this. Clear? Surface tension behaves like this. Got the idea up to this point? Yes? Okay. Now things are clear up to now. Okay. Complete your tute. Complete your tute. Write down anything important. Write down any important factor. Okay. Uh, Next. Now we know how to calculate the surface tension force. Okay. But when you try to calculate a force, not only the magnitude, you need to figure out the direction too. Okay. You need to figure out the direction too. Okay. That means if the liquid shape is like this, okay. If the liquid shape is like this, okay. Here this wall feel a surface tension of T in this direction. Clear? If you keep a pencil here, that pencil will feel a tension in this direction. If you place something here, that something will feel a tension in this direction. See? So we need to figure out not only the magnitude, now the magnitude is okay, the direction too, okay? Not only the magnitude, but the direction also we have to figure out. Clear? We have to figure out the direction too. Clear? So, uh, when you try to figure out the direction, okay? When you try to figure out the direction, what matters is the contact angle. That means think about a surface. Think about the particles here. Okay. It will feel, assume this is glass and water. It will feel a force from the glass and a force from the liquid. There will be a force from air too. This is air, this is water, this is the barrier, maybe glass. This we can forget, right? A very weak force. Air will exert a very weak force on this particle, so we can forget that. Clear? So when you consider this setup, on this liquid particle, if the glass create a higher force than the other liquid particles, clear? If the glass provides a higher force on this particle than other particles, clear? The resultant would be, when you solve these two, This minus this, you will have a small force like this, clear? Then you will have this one too, clear? Clear? Then the resultant of these two would look like this. Resultant of these two would look like this. Somewhere like this. Clear? Clear? So if a system need to be stationary, now due to this force, the liquid will move here and there, right? Due to this force, the liquid layer will move here and there due to this resultant force, clear? A system will stay stationary under a given force. I mean, when there's a force, a system will definitely move, right? Clear? But only when the possible movement of the object and the force is perpendicular, then only a particle can stay stationary under a force, right? When you apply a force on a particle, it can still stay stationary only if its possible movement is perpendicular to the force, right? If its possible movement, possible direction of motion is perpendicular to the force, it can stay stationary. So here also this particle will move here and there, and that particle will adjust itself in a way that it is perpendicular to this force. Then only the particle can stay peacefully. This is not actually included in the syllabus, so you don't have to focus on it. They will not ask, but I have to explain how it happens, okay? Otherwise, no point of telling, okay, when there's a class, there's what it looks like this. It's just a story, right? I need to tell the scientific background. That's why I tried to explain this. If you didn't understand this, don't worry about that. It's anyways not included in the syllabus, okay? So that's why you have seen this, right? When water touch the glass, at that contact point, it inclines a bit, right? Clear? It inclines a bit like this when water touch the glass, right? Clear? It's due to this, okay? To keep itself perpendicular to the resultant force, then only it can stay peacefully. Keep its membrane perpendicular to the resultant force, clear? So the story is, if the forces from the glass on water is stronger, then the liquid surface would look like this, clear? Then the liquid surface would look like this, clear? Clear? If the glass and water creates equal forces, that means forces by the glass or the container on the particle and the forces by the liquid on the particle, if they are actually same, then the surface would look like this. If the forces on this particle by the liquid is stronger than the forces by the container, then it will look like this. This is how you would see if you put mercury. Why? Mercury is a metal. Mercury creates very strong forces between them, right? Between their particles. So the cohesive forces among mercury would be much stronger. So the liquid surface will behave like this, clear? But when you put glass and water, glass creates a higher force. So the surface would look like this, clear? Clear? So when you put, if the forces by the glass on the liquid is stronger, it will look like this, or the container. Forces by the liquid is stronger than the forces created by the container, it will look like this. If they are almost same, it will look like this, clear? That is the rough idea, clear? Still, this is a qualitative quantity. You can't just tell, okay, it looks like this. So we need a proper measurement. We introduce a term called contact angle. Contact angle. That means we draw a tangent to the liquid surface here, clear? We draw a tangent to the liquid surface here. Then we measure the angle between this wall and the tangent through the liquid, clear? We measure it through the liquid, clear? We measure the angle between the wall and the tangent through the liquid, clear? This angle, okay, this angle, we call this the contact angle, clear? Here the contact angle is small. Here, what is the contact angle? You draw a tangent to the liquid surface, then you definitely measure it through the liquid, okay? Otherwise, you can measure it like this, okay? Then different people will get different answers. So the rule is you draw a tangent to the liquid surface, then you measure the angle between the wall and the tangent through the liquid. This will give a larger angle, right? This will give a larger angle, clear? This we call contact angle. So here the contact angle is 90. Here it's a small angle, here that is a large angle, and here it is 0. See, here it is 0, clear? Here the contact angle is 0. Got the idea? Ah. Now you have a proper method to for calculations. That means now if you have a wall like this, if you have a wall like this, if you have a wall like this, and if there's a liquid touching that, if there's a liquid touching that, clear? If there's a liquid touching that, if the contact angle is theta, if the contact angle is theta, now you can calculate, right? How? If the length is L, total surface tension on the wall would be total surface tension on the wall would be T into L, right? T into L. Like that you can calculate surface tension coefficient into length, you get the total force, clear? Assume you have liquid from both sides. Assume you have liquid from both sides. Then this side and the other side is also in contact, right? So then it becomes 2 into TL, clear? But when you have liquid in both sides, this horizontal component and this horizontal component will cancel out each other, right? These horizontal components will cancel out each other. Then only the vertical components will remain, right? Clear? So how to get the vertical component? Now you know the contact angle. So it is cos theta. It is cos theta. So the overall force will be 2TL into cos theta downward. See, that's how we do questions, okay? That's how we analyze questions, clear? You use the length to get the force, and whenever you need to get components, you use the contact angle, clear? That's how we connect things to come up with answers, clear? Go to exercise 4. Go to exercise 4. Go to exercise 4. Question 1, 2, 3. Question 1, 2, 3. Exercise 4. Question 1, 2, and 3. Okay. Exercise for question 1. Exercise for question 1. A rectangular block of glass length A and width B is immersed in a liquid so that the part of the block is above the liquid surface. If the surface tension coefficient is T and the angle of contact is theta, find the effective surface tension force acting on it. Okay, so this is the system. A rectangular block of glass length A and width B. Length A and width B immersed in a liquid so that the part of a block is above the liquid surface. Uh, so, angle of contact theta, find the effective surface tension. So, if you consider these two sides, liquid would look like this, right? It will look like this with an angle of theta. Clear? And this surface tension force would be T. What is T into what? T into A. Clear? But there are two sides. There are two sides. This side A and the next side A. Clear? So you have to multiply it by 2. Clear? You have to multiply it by 2. But while multiplying it, the horizontal components will cancel out, right? It will never move horizontally. No horizontal force. See? Why? This T sine theta and this T sine theta will cancel out. So only the cos theta components will remain, right? Only the cos theta components will remain. Clear? So you multiply it by cos theta. Cos theta. Clear? Then you will get a similar incident from this B and that B, right? You will feel a similar set of forces from this B and that B, right? Clear? So you can write T into B into 2 cos theta. Clear? Clear? Then you will get 2T cos theta. You get 2T cos theta A plus B. 2T cos theta A plus B. Clear? You get 2T cos theta A plus B. This is the overall force. Clear? And it is downward. It is downward. Let's go to question B. Let's go to question 2. Let's go to question 2. You have a cylinder like this. You have forces surrounding from all the sides. Okay. You have forces surrounding from all the sides. And what would be the length of contact? It's surrounded like this. It's surrounded by liquid like this. And it is touching the liquid surface from around. Clear? It is touching the liquid surface from around. So how do you get the force? You get the force by multiplying the surface tension coefficient by the total length of contact with the liquid. You take the total length of contact with the with the liquid and multiply it by the surface tension coefficient. So you get T into what is this surrounding length? 2 pi r, right? Surrounding length is 2 pi r. In this case, it is 2 pi a. In this case, the surrounding length is 2 pi a. In this case, the surrounding length is 2 pi a. Clear? Surrounding length is 2 pi a. But again, the horizontal components will cancel out. Only the vertical components will remain. Clear? So you again have to multiply it by the cos of the contact angle, which is cos theta. Clear? You again have to get cos theta to come up with the final answer. Clear? Clear? This is the final answer. T into 2 pi a cos theta. Clear? Let's go to question 3. Let's go to question 3. Quickly try to get the answer for 3. Okay. Question 3. Question 3. This is a ring. This is a ring. So when you just put a ring in water like this, okay, it touches water from this circle and this circle both, right? Here also under contact with water. Here also under contact with water. Here also it's under contact with water, right? Clear? Both this circle and this circle. Clear? Then uh, mass M, mass M. Now the story is this, okay? Now this ring will feel a weight of mg. Clear? Have you felt this when you try to get something out of water? Just at the surface, you have to give an additional impulse to remove that. When you try to remove something out slowly from water, just at the surface, you have to give an additional impulse. Why? When it is in the water, there's no surface tension. There's no surface tension in the water. But when it reaches the surface, it is dragged by the surface tension. You have to give an additional pull to remove that. Clear? This is a very slight force, okay? So, additionally to this mg, you have to withstand this surface tension to get rid of, to remove this from water, okay? So it is mg and the surface tension force. So this F should be equal to the weight of the ring plus, what are the values of radius? Inner radius A, outer B. Inner radius A, outer B. So this 2 pi A inner radius is in contact with water, and 2 pi B outer radius is also in contact with water. Both 2 pi A and 2 pi B is in contact with water. Clear? Both 2 pi A and 2 pi B is in contact with water. Clear? This circle and this circle. Clear? Clear? Then you multiply it by the surface tension coefficient, which gives you the force. Then the surrounding horizontal components will cancel out. Only the vertical forces affect the pull, right? So you just have to get cos theta to get the downward component of all the forces. Clear? This is the answer. Clear? Clear? So now in this lesson, what we are doing is we are analyzing different scenarios that may happen due to surface tension. Clear? Different practical scenarios that may occur due to surface tension. Clear? Different practical scenarios that may occur due to surface tension. So in this case, okay, in this case, uh, when talking about different practical scenarios, okay, when talking about different practical scenarios, one of the main practical scenarios that occur due to surface tension is this bubble shape of water, right? This bubble shape of water. That means not water actually. If a gas bubble appears in water, it takes this bubble shape, right? Clear? And even if you blow a soap bubble in air, it will look like a sphere, right? What is the reason for this? This is a gas bubble. This is a gas bubble in water. Clear? A gas bubble in water. So here, okay, here, for anything to get this bubble shape, there are two conditions to satisfy. For anything to get this bubble shape, there are two conditions to satisfy. What are they? What are the two conditions? One is there must be a pressure difference, right? When you blow a balloon, okay, it gets this shape because you increase the pressure inside. So for anything to get this bubble shape, it need an additional pressure. So there should be a pressure difference inside and out. And there should be someone holding this pressure difference. In the rubber, that rubber is holding it by tension. So there should be some kind of a tensile force, tension force, holding this pressure difference. Clear? So in this case, that pressure force is the surface tension appears here. Okay. That pressure force is the surface tension which appears here. Clear? Pressure force is the surface tension that appears here. Clear? Got the idea? Ah. Clear? So now, if we do a proper analysis, let's try to analyze this. I'll consider half of this sphere. Okay. If I cut it like this, it will look like this, right? So, who's holding this half of the sphere and this half of the sphere? The surface tension appearing here and here. So, they are stick together by the surface tension between them, right? They are stick together by the surface tension acting between them, right? They are sticked together by the surface tension acting between them, right? It's held by the surface tension, clear? So we know who's behind this force. It's the surface tension which is holding this shape. Clear? Clear? And you have an internal pressure P1 and external pressure P2. Clear? And that additional pressure inside will produce a force in that direction. That means the pressure will appear here like this. Okay. This is P1 minus P2. The P1 is larger. So a resultant will appear like this. But the vertical components will cancel out, right? See? Vertical components will cancel out. Only the horizontal components will remain. Clear? Only the horizontal components will remain. So the result, there will be a resultant horizontal force like this. Clear? Who's holding this resultant horizontal force? The surface tension force that appears in this band. Clear? So, if the radius is r, what is this surrounding length? 2 pi r, right? This length is 2 pi r, right? It is the cross section of a sphere. So, this surrounding length is 2 pi r. 2 pi r into you multiply it by the surface tension coefficient. Clear? 2 pi r, you multiply it by the surface tension coefficient, which gives you the total force. Clear? 2 pi r, you multiply it by the surface tension coefficient, which gives you the total force. Clear? It's balancing this pressure difference. What is the pressure difference? In pressure inside P1, pressure outside minus P2. To get the force, you should multiply this by area. So since all the vertical components cancel out, only the horizontal area matters, right? Only the horizontal area matters. What is the horizontal area? If you turn on a torch from this side, you will get the horizontal area on a wall, right? Okay. If you on a torch from this side, you will see the horizontal surface area on the wall, which is an area like this, which is pi r squared, right? Which is pi r squared, right? Which is pi r squared. Clear? So this area becomes what? This area becomes pi r squared. Clear? This area becomes pi r squared. Got the idea? Area becomes pi r squared. Okay. So you get 2 pi r into t equals p1 minus p2 into pi r squared. Clear? So then pi cancels out. 1 r cancels out. This is pressure difference, which is delta p. Here you have 2t over r. Clear? Delta p equals 2t over r. Clear? So this is this is the equation of formation of a bubble, air bubble in water. 2t over r. Clear? So higher the pressure difference, smaller the radius. Higher the pressure difference, smaller the radius. Clear? Ah. I'll directly go for a soap bubble too. Soap bubble is quite different. Why? If you cut a soap bubble from half, it will contain two surfaces. Why? For a gas bubble in water, everywhere you have water and only inside you have gas. Okay? So it's just gas water surface, one surface. But a soap bubble floats in air. So you have air, then soap, then again soap and air. See? So a soap bubble holds two surfaces, right? Air, soap, soap, air. Clear? And the radius is almost same. Radius is almost same. So if you do the same calculation, to a soap bubble, it's the same thing, but only thing is you will have two surfaces here. Clear? So when you write the surface tension, it is 2 pi r into T, but there are two surfaces like that, so you multiply it by 2. Clear? There are two surfaces like that, so you multiply it by 2. Clear? And here you have P1 minus P2, then pi r squared. Clear? Pi r squared. Clear? Then pi cancels out, r cancels out. Then you have P1 minus P2 means delta P. P1 minus P2 is delta P equals 40 over R. Clear? So for a air bubble in water, it is 2T over R. For a soap bubble in air, it is 4T over R. That is the only difference. Clear? So another practical scenario that occurs due to surface tension. Clear? Another practical scenario that occurs due to surface tension. Go to exercise 5, question 3. Go to exercise 5, question 3. 4 and 5. 3, 4 and 5. Try to come up with the answers. Question 3. Exercise 5, question 3. The pressure in a soap bubble in air is greater than P. Pressure in the surrounding air. The pressure of the bubble of water is 3P higher than the surrounding pressure. If the radius of soap bubble is twice the radius of the water bubble, the surface tension of water, find the surface tension of soap solution. So there's a soap bubble and a water bubble, air bubble in water and a soap bubble. So for this delta P pressure difference is 2T over R, and for the other one it is delta PU equals 4T over R. So in the water bubble, what is the pressure difference? For the soap bubble, it is pressure difference is P. For the water bubble, it is 3P. Then here you have 2 into T. What is T? Surface tension coefficient. What is the surface tension coefficient? Radius of the soap bubble is twice. So here you have the water surface tension. Here you have the surface tension of soap. Then what is twice? Radius of soap bubble is twice the radius of water bubble. Radius of soap bubble is twice the radius of water bubble. So this is the water bubble. Radius of the soap bubble is twice the radius of water bubble, right? So now you have the answer. You just divide these two, divide this by this. 3P over P equals here 2 TW over R, here 4 TS over R. P cancels out. TW and R cancels out. Sorry, TW doesn't cancel out. 2 and R cancels out. 2 cancel out with 2 and R. Then you have 3. 3 in this side. Here you have equals TW over 2 into TS. 2 into TS. Then you get TS equals what? TS equals TW over 6. TS equals TW over 6, which means what is TW? Surface tension of water, right? What is TW? TW is 72 into 10 to the power minus 3. 72 into 10 to the power minus 3 over 6. This is the surface tension of soap. Clear? Next one, question 4. Go to question 4. Go to question 4 quickly. So what is the next one? Question 4. Next one is question 4. Next one is question 4. Question 4. Two soap bubbles radius 3 centimeter and 4 centimeter in the same soap solution from a single bubble with each other under isothermal conditions. Find the radius of this bubble. So in this scenario, uh, two soap bubbles radius 3 centimeters. Here the radius is 3 centimeters and here the radius is 4 centimeters. So in a question like this, okay, in a question like this, I mean, this is not actually a surface tension question, okay? Okay, this is not a surface tension question. You have to, and there are two ways of analyzing these things. I'll just teach this as a theory point. Think that there are two air bubbles. That means air bubbles in water. When they connect with each other, what happens is the total air volume be same, right? So what is the air volume here? 4/3 pi r1 cube. Here, if the radius is r1. If the radius is r2, here 4/3 pi r2 cube. Clear? And the total volume will be equal to this. 4/3 pi capital R cube. Clear? Will give you 4/3 pi capital R cube. Clear? So use all this and you get capital R. When it is two soap bubbles, what happens? The amount of soap is the thing that gets conserved. Here amount of air, right? Because you can't get air out from water. So the amount of air is same. Here it is amount of soap. Amount of soap. So when they combine and create one soap bubble, you consider the total surface area as constant, because in the surface area you have soap. So if you, what is the surface area of this? 4 pi r1 squared. What is the surface area of this? 4 pi r2 squared, which is equal to 4 pi capital R squared. Clear? So these are soap bubbles, right? These are soap bubbles, right? So you write 4 pi 3 squared plus 4 pi 4 squared equals 4 pi capital R squared. Clear? 4 pi cancels out, 4 pi cancels out, 4 pi cancels out. Then capital R becomes 5, right? Centimeters. Clear? Clear? So this is not a surface tension question, but you may need this in many other questions, okay? That is the idea. Go to question 5. Go to question 5 now. So question 5. Question 5. Two soap bubbles, radius R1. There's one soap bubble, radius R1, and another soap bubble, radius R2. Another soap bubble, radius R2. Another soap bubble, radius R2. Clear? One soap bubble, radius R1, another soap bubble, radius R2. Clear? Definitely the smaller one has a higher pressure, right? You have seen what happens when two soap bubbles get together. What happens when two soap bubbles get together? You have seen this, right? They form a shape like this. Have you seen this? When two soap bubbles get together, they try to form a shape like this, right? Clear? Then it has a membrane like this, a membrane like this, and they have a common interface like this, okay? They have a common interface like this, clear? So the radius of this one is R1, radius of this one is R2, clear? Radius of this one is R1, radius of this one is R2, clear? And the common surface would look like this, clear? Common surface would look like this, clear? Common surface would look like this. Common surface will have a different radius, okay? Common surface will have a different radius. I'll call that capital R, clear? Common surface will have a different radius, clear? So what decide these radius values? Outside the bubbles, you have the atmospheric pressure. Here inside you have P1. Here inside you have P2, clear? So since these are soap bubbles, you can write P1 minus P naught. You can write P1 minus P naught. You can write P1 minus P naught equals 40 over R1. Clear? Here P2 minus P naught. P2 minus P naught equals 40 over R2. P1 minus P2 40 over R1. P2 minus P naught 40 over R2. Then what decides this common interface? P1 minus P2. What decides the common interface? P1 minus P2. Clear? Which is equal to what? 40 over, what is the radius of the common interface? Capital R. Clear? 40 over capital R. Clear? So I can use this to create that, right? How? I subtract this equation from this equation. So I get P1 minus P naught here minus P2 plus P naught. I subtract this by this equals 40 over R1 minus 40 over R2. Then P naught cancels out. I have P1 minus P2. I have P1 minus P2 equals 40 over R1 minus 40 over R2. Clear? So here you can put P1 minus P2 equals 40 over R1 minus 40 over R2. P1 minus P2 is 40 over R1 minus 40 over R2 equals 40 over capital R. 40 cancels out. 1 over R1 minus 1 over R2 equals 1 over capital R. Then you get R2 minus R1 over R1 R2 equals 1 over capital R. R equals R1 R2 R2 minus R1. Clear? 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 Like that you can do calculations. Let's analyze another application. Let's analyze another application. Let's analyze another application related to surface tension, which is, but I mean, if I move forward a bit with this bubbles scenario, it need not to be a complete sphere, okay? It need not to be a complete sphere. Write this down quickly if you had write down anything. Okay. Uh, like this need not to be a like actually there's no like necessity of having a sphere. Okay. Sometimes you have seen even when you are like when you are using a straw to create a soap bubble, when you blow here, it will create a shape like this, right? Why? Here and here there's a pressure difference. Okay. Here and here there's a pressure difference. Okay. So even in scenarios like this, okay, even in scenarios like this bubble shape appears. Okay. It need not to be an entire sphere. So let's like just think what happens when you try to blow a soap bubble in a straw. Initially the soap membrane looks like this. Okay. Clear? Now you blow this side and increase the pressure of this side. Then what happens? Slowly it starts creating a spherical shape like this. Clear? Clear? Then when you increase the pressure further, when you increase the pressure further, it becomes a much smaller sphere, right? It becomes a much smaller sphere. Then you increase the pressures further. When you increase the pressure further, it becomes like this, having the exact radius as the tube. Can you have a smaller radius than this? This is a soap bubble, so delta P equals 40 over R. This is the smallest possible radius you can get, right? If you try to reach a smaller radius than this, then you can't stay in contact with the straw, right? Okay, so you get the smallest radius when the radius of the bubble is equal to the radius of the straw. Clear? That is the smallest possible radius. Clear? That is the smallest possible radius. Clear? When the radius of the bubble is equal to the radius of the straw. Now, if you try to blow further and increase the pressure further, what happens? The system can't withstand this anymore. Okay, system can't withstand this anymore. So the bubble will come out and will go out as a bubble. Clear? Eventually would go out as a soap bubble. Clear? That's how a soap bubble is formed. Clear? So what actually happens is if we check the pressure inside, you keep increasing the pressure and reach here. This is the maximum possible friction. After that it comes out and decrease the pressure by itself. Clear? You keep blowing this, keep increasing the pressure, and here it can't withstand anymore. It comes out, put some air out and create a smaller bubble. Clear? So this is how the pressure behaves. And the radius also the same thing. Okay? Radius also, when you increase the pressure, radius keeps decreasing. Then it can't handle it anymore after this point. Then it comes out and create a bubble by increasing the radius a bit larger. That means having a smaller pressure. Clear? Got the idea? I just explained a practical scenario using the concepts we already know. Okay? Clear? Got the idea? Okay. Next. Next. Another practical scenario that occurs due to surface tension is capillary rise. Okay, even in trees, water goes up at water reach very high heights, right? I mean, surface tension can't do this alone. There are negative pressure kind of stuff you have in your bio book, right? There are negative pressure kind of stuff, but surface tension do at least a small part of the job. That means a small tube, a small capillary tube, have the capacity to move liquid up through that tube. Clear? How does this happen? You know, in a container, if you have a liquid, it may appear like this, right? It may appear like this, right? Clear? But when you make this container small, very small, this half circle part will meet this half circle part, which together they will create a meniscus. Clear? Clear? When this happens at the liquid surface, okay? Now you have the liquid here, the meniscus will be formed here, and you have the liquid here. Clear? So here the pressure is atmospheric pressure P naught. Clear? Then here also the pressure is P naught, right? Clear? P naught. Because it's just below that point. So here also the pressure is P naught. Clear? Same here. P naught. And here P naught. Clear? Okay. Now the problem is there are some kind of a meniscus like this. That means some kind of a circular shape. Clear? And here this is an open end. So here also you have P naught, right? Clear? P naught. And if the pressure here is P1, if the radius of this is R, you can write P naught minus P1. This is water. So 2T over R. 2T over R. Clear? Then you get P1 equals P naught minus 2T over R. Clear? Clear? So here you have P naught. Here you have P1, which is P naught minus 2R, 2T over R. Here P naught. This is breaching a fundamental, right? Why? At the same liquid level, you must have the same pressure. At the same liquid level, you must have the same pressure. Here P naught, here P naught, here a different pressure. This is a breach of fundamentals, right? So what actually happens is these sides have a higher pressure than here. So these sides will push the liquid down and this liquid column will move up. This liquid column will move up like this. Clear? How far will it move up? How far will it move? If the height is h, how far will it move? Here the pressure is P naught, right? So fundamentally, pressure here also must be equal to P naught, right? Here it is P naught again, clear? Then here it is P naught minus 2T over R. 2T over R. Then here it is P naught minus 2T over R plus H rho G. Clear? Here it is P naught minus 2T over R plus H rho G. Clear? So here you have P naught minus 2T over R plus H rho G. Clear? Is equal to P naught. Clear? Is equal to P naught. Clear? P naught minus 2T over R plus H rho G is equal to P naught. It should be like that, right? So P naught and P naught will cancel out. So H is equal to 2T over R rho G. Clear? H is equal to 2T over R rho G. This is how you get the capillary rise. We call this the capillary rise. Clear? This is the height. Okay. Complete your tute. Write down if you have to write anything. Okay. H equals 2t over r rho g. Sometimes this is not that convenient, this type of an equation. Why? What is this r? What is this r? R is the radius of the meniscus, and you always don't know this radius, right? Clear? You always don't know this radius, okay? R is the radius of the meniscus, and it is pretty difficult to measure this radius too, okay? It's pretty difficult to measure this radius of the meniscus, okay? Clear? Clear? It's not easy. So we modify this equation a bit. We modify this equation a bit like this. So this is the radius. That means it's a large circle. Clear? This is its center. This is the radius that we have here. Clear? And this is the radius of the tube. This is the radius of the tube. Clear? This is the tangent, and this is the contact angle theta, right? If this is theta, this is 90, so this is 90 minus theta, right? If this is theta, this is 90, so this is 90 minus theta, right? If this is 90 minus theta, this is again theta. Clear? This is again theta. Clear? So you write cos theta equals what? Cos theta equals capital R over simple r. Capital R over simple r. Clear? So now instead of simple r, you can write capital R over cos theta. This is much convenient. Why? You know capital R, you can measure the radius of the tube. And at the same time, you can find the contact angle by searching. You can search the contact angle between liquid and glass. You will get the value. So it's much convenient to replace simple r by that. So we will replace that part. Then we will have 2t over rho g. Instead of r, we have capital R over cos theta. So then we will get 2t cos theta, 2t cos theta over r rho g. Clear? You will get 2t cos theta over r rho g. Clear? You will get 2t cos theta over r rho g. So this is the capillary rise. Capillary rise. Clear? So for many liquids, this theta is something like 60. This theta is something like 60, 40, 45, 30. No big issue there. But for some liquids, this contact angle is something like 120. Clear? For some liquids, this contact angle is like 120. So the problem is cos 120. Cos 120, okay? Cos 120 is a negative value. Cos values larger than 90 are negative, right? Cos values between 90 and 180 are negative. So here if you put cos 120, you will get a negative answer. What is the meaning of that? It's not actually going up. It's not actually going up. If this is the liquid level, it goes down. This is a capillary depression. So mercury would go down, not up. Clear? Clear? So that is the meaning of that negative mark. And especially for bio people, like finding cos 20 you may find hectic. So what you should do is, if this is 120, find this angle. What is this one? If this is 120, this is 60, right? If this is 120, this is 60, right? You just put that. H equals 2t cos 60 over r rho g. Clear? Okay, no big issue. You get the same answer. You just put this angle. But you won't get the negative mark then. But you know the meaning of the negative mark. You know when it is like this, it will go down. So you mark it properly, then you don't need the negative mark, okay? If you mark it below the water level and show a diagram properly, then they know that you have already identified the capillary depression. When you have already identified the capillary depression, you don't have to worry about the negative mark. You just write the equation. You just put the angle here. Clear? Got the idea? Like that you can work with this. Okay? Then at the same time, okay, Then at the same time, like you can prove this like this too. Okay, if you like, you can prove it like this too. Think like this. Now I'll think that the surface tension is lifting this weight. Another method, surface tension is lifting this weight. In that case, what is the surrounding area? 2 pi r. R is the radius of the tube. Clear? This surrounding area is 2 pi r. Clear? Clear? 2 pi r means this surrounding. Clear? This surrounding circumference. Clear? That's where the liquid touch the glass, right? There you have the surface tension. Where the liquid touch the glass, you have the surface tension. Clear? Then you multiply it by the surface tension coefficient to get the value. This will provide the force on this part. Then you have the contact angle, which is theta. Then you have the contact angle, which is theta. Clear? Theta is here. If theta is here, theta is same here, right? So you are lifting this up, right? So you have to take this component, which is t 2 pi rt cos theta. So this is the overall surface tension force acting up on this liquid column. Clear? This surface tension force is lifting the weight of this part. This surface tension force is lifting the weight of this part. What is the weight of this part? What is the area? Area is pi r squared. Area is pi r squared. Sorry, it's capital R. Pi r squared multiplied by the height. Clear? So you get pi r squared into h, which is the volume, into density, rho, gives you the mass into g. Clear? So what is the value h? Pi cancels out, r cancels out, h is 2t cos theta over r rho g. You get the same answer. Clear? 2t cos theta over r rho g. Clear? You get the same answer. See? Like that you can prove this using two scenarios. Go to the questions. Exercise 5, question 6. Go to exercise 5, question 6. And 8. And 8. Go to question 6 and 8. Okay. Uh, exercise 5, question 6 and 8. Exercise 5, question 6. The length of a cane capillary tube 0.8 millimeter in diameter is 6 centimeters. The capillary tube. We have a capillary tube. Capillary tube. Diameter is, what is the diameter? 0.8 millimeters. The radius means, then the radius is 0.4, right? Radius is 0.4. Clear? So what is the height then? What is the equation for the height? 2t cos theta over r rho g, right? Clear? So you have 2. What is t? What is t? 72 into 10 to the power minus 3. What is cos theta? Contact angle is 0, right? Cos 0 means 1. What is the radius of the tube? 0.4 millimeters. 0.4 millimeters. Rho density 1000. G 10. 2 point. Okay, by solving this we get 3.6 centimeters. Okay, so the water will lift up to a height of 3.6 centimeters. The next thing they are asking is, what if this height is only 3? What if the tube ends at 3? This need to reach a 3.6, but we only have 3. I mean, water won't go like this, right? Okay, it won't behave like this. Okay, it won't behave like a water flower. Okay, what would happen here? It won't behave like a pump in this scenario. It will just adjust its angle here according to 3 centimeters. It will just adjust its angle here according to 3 centimeters. Clear? So there are some specific scenarios like this. We can artificially change the contact angle. See, this is a specific scenario where we artificially change the angle. Clear? Then when you bring this down, what happens? When you bring this down, eventually it gets flat. Clear? Eventually it gets flat. Clear? Got the idea? That is the idea. Eventually it becomes flat. Okay? Ah. Question 8. Question 8. Write this down. Write this down. Question 8. Question 8. Uh, so, like, when you fill the water to a container like this, it will like, it won't straight go out like this. Why? because it can form a bubble using surface tension like this and withstand the pressure difference, right? So if the pressure here is P naught, pressure here will be, if the height is h, pressure here will be P naught plus h rho g. Then the pressure here is P naught. Then this pressure difference P naught plus h rho g minus P naught equals what? 2T over R, clear? The pressure difference h rho g, pressure difference h rho g will be held by the surface tension bubble, clear? By the surface tension bubble. But the thing is, there's a, so lower the radius, higher the height it can withstand, clear? But there's a smallest value that this radius can get. What is that? Radius of the hole. Smallest radius is radius of a hole, right? Radius of the hole. So you get h equals 2t over r rho g, and h max, maximum height that can be balanced, will be given when the radius is at its smallest, which is the radius of the hole. So you get here 2. What is the surface tension? What is the surface tension? Sorry? 7.3 into 10 to the power minus 2. What is the radius of the hole? What? 0.1 millimeter. 0.1 millimeter. Hope this is water, which means 1000. G means 10. G means 10. Clear? Clear? So what do you get when you solve this? What do you get when you solve this? 2 into 7.3 into 10 to the power minus 2, 0.1 into 10 to the power minus 3 into 10 to the power 3 into 10. You get 0.146 meters, which means 14.6 centimeters, right? You get 14.6 centimeters. So you can withstand a maximum height of 14.6 centimeters. What they're asking is, can we fill water up to 10 centimeters? Yes. Why? This can hold up to 14.6 centimeters of water. So 10 centimeters of water is okay. Clear? Okay. That's how we prepare this waterproof material, umbrellas, everything. Okay. We can never prepare things without gaps. Any material would have gaps, right? But we can alter it. Okay. We can alter the pressure it can withstand by changing the surface tension, changing the radius, like that. Clear? Clear? That's how the waterproof covers, rain covers kind of stuff are made. Clear? Ah. So there's one more theory point left to learn. The last theory point. It is actually two last theory points, very small theory points. One thing is, before moving forward, you should be able to analyze scenarios like this too. Assume like you are putting these kind of two plates into water. Then what happened? The water may rise like this, right? Water may rise like this. And this height is h. Clear? If the gap is d, and if this length is l, clear? You will see in this side you have TL cos theta. Clear? This length is L, so TL. Again, I need the upward force, so TL cos theta. You have a same side in that side, right? So TL cos theta and TL cos theta, overall force will appear upward by these two plates. How much of a weight it can balance? Length L, gap D, height h. This is the volume of the liquid that it raises up. You multiply it by density to get the mass. You multiply it by g to get the weight. Clear? You multiply it by the density to get the mass. You multiply it by g to get the weight. You solve this, you can find h. What is h? 2TL cos theta over L D rho G. Clear? Clear? Like that, even other scenarios you should be able to analyze. Okay. Then I'll explain few other practical scenarios. One more practical scenario here. Is this clear up to this point? Any questions? Anyone? Online students, please mention in the Zoom chat if you have any questions. Then just put them in the Zoom chat if you have any questions. Like think you have a soap solution. You put a string onto this, a loop, a string loop. You remove the soap in the middle. You use a brush or something like that and remove the soap in the middle. What happens? Initially, surface tension was acting like this from inside the soap and outside the soap both. Clear? But now when you remove the inside part, inside soap, you only have outside forces. Okay? You only have what? Outside forces. Clear? So this will eventually turn into a what? This will eventually turn into a circle by all the tension forces. Okay? Now if I need to find the tension in this string, what is the value? So the forces are acting in all directions. If I consider this half, forces will act like this by the soap. Clear? And this half is held by the, this half and this half is held by the tension between them. These two halves are held by the tension between them. Clear? Then what is the total force in this direction? What is the total force in this direction? You can forget the components in this direction, right? These components you can forget. So what matters is only the components in this direction, right? Clear? 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 So what matters is only this length, right? If what matters only the components in this direction, what matters is only this length, right? Which is 2r. Which is 2r. Clear? So this length is 2r. You multiply it by the surface tension coefficient to get the total force created in this direction by the surface tension. Clear? Now this is also T. This is not T. This is the internal tension of the string. I'll call that F, otherwise it will confuse with the surface tension. Okay. This surface tension force is held by the force inside the string. But that is not the entire surface tension force. Why? When you consider the soap membrane, if this is the string, you have soap above and soap below too, right? Clear? If this is the string, here you have air soap. Then below you have the table soap. There are two soap surfaces, right? Touching the band. Two soap surfaces. That means it's not just 2r, another 2r length like that. Clear? So to get the overall force, you have to multiply it by 2 because it's two surfaces touching. Okay? Clear? Then this total force is held by this F and this F, which is 2F. Clear? Which is 2F. So you cancel out 2, you get the tension as 2RT. These are not theory, these are just things that may appear in questions. Okay? Things that may appear in question. Clear? Like this, you can get the force inside the string. Okay? Like this, you can get the force inside the string. Let's move forward. One more thing, last theory point. In the beginning of the lesson, we learned that higher the surface area, higher the energy, right? So now what we are going to do is we are going to calculate that energy due to surface area. So I'll take something like this. I'll take two railings like this and I'll create a small soap membrane like this. I'll create a small soap membrane like this. Clear? So if this length is L, what is the total force by soap? What is the total force by soap? TL. TL. But this is just a frame like this. So you have two soap surfaces in both sides, right? You have two soap surfaces like this. So there are not just TL, 2 into TL overall force in this direction. Clear? There's a soap membrane going like this, and there's a soap membrane going from other side. Clear? So it's TL into 2. Two soap membranes, one from this side and the other from other side. Two soap membranes touching this railing. Clear? So it's not just TL, it's 2 into TL. Clear? Clear? So to drag this in this direction, you should provide an equal force to this force, right? You should provide an equal force to this one, right? Clear? Ah. Now under this force, if I drag this for a distance of x, what is the work done? What is the work done? Work done is force into displacement, right? Force into displacement. What is the force here? 2 into T into L. Force is 2 into T into L. Clear? Into displacement. What is the displacement? X. Clear? Displacement is X. Clear? 2 into T into L into X. This is the overall work done. Clear? This is the overall work done. Clear? Now, I'm going to introduce a term called free surface energy. Free surface energy means how much energy is stored per unit area of a liquid surface. Okay, because if I find this free surface energy term, I can directly multiply it by area and find the stored energy. I'm going to introduce a term called free surface energy, which is energy stored in a unit area of a liquid. Clear? So in this case, due to this work, the area increases, right? What is the increased area? L into X. But it's not just L into X. It's an area from this side and the area from the other side, right? So 2 into L into X, right? Overall area from this side and the other side. Clear? You get the area, multiply it by, free surface energy to get the total stored energy. Clear? Clear? This is the area. Free surface energy is a new term which represents the energy per unit area. So you get energy per unit area, multiply it by area, you get energy. Clear? You get energy per unit area gamma. You multiply it by area to get the energy. So this work done is the stored energy. So these two are equal, right? This work done is stored energy. So these two are equal. Clear? So here what you would get is now X will cancel out. L will cancel out. Then you will have 2 will cancel out. Gamma equals T. So free surface energy is equal to the surface tension coefficient. So if someone asks you the surface energy stored in this sphere, what is the surface energy? 4 pi r squared. 4 pi r squared, which is the surface area. You multiply it by surface energy. You get the total energy stored in this sphere. Clear? And this gamma is equal to the surface tension coefficient. Gamma is equal to the surface tension coefficient. Clear? Then at the same time, there are some scenarios like this too. Okay. Like sometimes they may give questions like this. You have, I'll give you this question. You have a sphere with a radius r, a small spherical water bubble. You get 8 water bubbles like that get together and create one huge water bubble. Okay. Uh, Specific heat capacity of water is C. Okay. Density of water is rho. Find the increase of temperature when it turns into one bubble. Find the increase of temperature when it turns into one bubble. Try to find that. Okay. So how do you analyze this one? These are water bubbles, right? Did I mention that they are water bubbles? Yeah. So water bubbles means the water volume is constant, right? Water volume is constant. So what is the water volume here? 4 over 3 pi r cube. And there are 8 cubes, 8 bubbles like that. And all together will create a radius capital R, which is 4 over 3 pi capital R cube. Clear? So 4 over 3 and pi will cancel out. R cube equals 8 into simple R cube. Then capital R equals 2R. Clear? Clear? Then what is the energy difference? This is the idea. Initially, what is the total surface area? Surface area of one bubble is 4 pi R squared. Here. Into 8 bubbles like that. You multiply it by the free surface energy, gamma, which gives you the energy of the surface. Now the energy is 4 pi capital R squared, one bubble, multiplied by gamma. Clear? Multiply by gamma, free surface energy. Clear? I'll take gamma out. 4 pi out. Here you have 8 simple R squared. Here you have capital R. Capital R is 2R. So you have 2R squared. Clear? So you get 4 pi gamma 8R squared minus 4R squared. Clear? Then you get 16 pi gamma. I can write as T, right? Gamma is equal to surface tension coefficient. Gamma pi T. Here you get 4R squared. So this is the energy difference, right? That means initially I had a higher energy. Now I had a smaller energy. There's an energy drop. So surface energy drops. What happens to this energy? In this question, I can assume that this energy converts into heat energy. In this question, I can assume that this energy converts into heat energy. If energy drops, it should be converted into other energy type. I can assume that it turns into heat energy. So Q equals then mc theta. Clear? Q equals mc theta. So here you have 16 pi T 4 R squared. Here, what is the mass? Total volume 4 over 3 pi capital R cube. Capital R means 2R. This is the total volume. Multiply by density to get the mass. Multiply by density to get the mass. Specific heat capacity C. Temperature difference theta. You solve this, you get theta. That's how you get applications from the surface tension. Clear? Sorry, surface energy, free surface energy. So when you solve this, you get pi cancels out. I'm not going to do all the calculations. 4 cancels out. 48 over 8. R cancels out. You have T here. 1 R left here. Rho C. Clear? Clear? This is the answer. Clear? You can do calculations like that. Clear? So the plan is finish all the exercises. I'll provide the practicals as a recording. A small recording would be sufficient and 1 hour recording. Then I'll let you know I'll give like 1.5 or 2 weeks to try all the questions, finish all the questions, and I'll provide a past paper recording too. Past paper and then let's arrange a online or physical session to do the past paper questions and the remaining questions in the book. Okay. So officially the theory is over. Thank you.